Okie dokie, okie dokie. So, hello, and welcome to our next lesson. Today we are talking about curve sketching again. Pretty much what we did in the last lesson, but today we're going to be looking at examples of different types, mostly rationals. Okay, so how to use the first and second derivative and the original function to help us graph rationals and get a nice, accurate picture. Okay, so right here you got yourself a little warm up. And this warm-up is like the example we left off with in class yesterday. So like that free response, it is giving you the graph of the derivative. So see if you can use the graph of the derivative to answer these questions, and we'll do it in class. All right, and no gateway, unfortunately. So let's read through a few of these notes, and then we'll do, my goal is to get through like 2 examples and then finish the rest in class. It says, plotting points to a graph, a function, can give you an incomplete picture of the graph. Points are just points. It tells you nothing in between. Even the calculator can be misleading sometimes if you do not have the right window. And sometimes it doesn't show holes. Sometimes it doesn't show asymptotes correctly. Sometimes the graphing calculator isn't the best tool. We use our graphing calculator as a tool for checking our work. Okay, so I know I don't have control over calculator active and inactive questions with you at home. The graphing calculator is meant to be just a tool, all right? I've already kind of gone over the points that I expect you to be plotting and how to be graphing these in our last lesson, and I'll be re-emphasizing those today. All right, so our guidelines for sketching a curve. So this is somewhat of a review, as well as some new stuff today. So the following checklist is intended as a guide to sketching a curve by hand. Not every item is relevant to every function, okay? But I'll tell you all the stuff that I do look for. This is a pretty good list. I don't always do number 1, but I try to stick with it sometimes, and that's determining the domain. So finding where X is defined, and that's going to be mostly applicable for today, where we're talking about like asymptotes and stuff like that, so where X cannot be equal to. So I think doing number 1 is pretty helpful here. But number 2, I usually try to do, determine X and Y intercepts. Okay. Although this is very helpful, if the equation is too difficult to solve, then you can omit this step. But I usually try to find the X and Y intercepts as well. And this is more so for today's lesson, number 3. I try to determine the vertical and horizontal asymptotes. Okay, so that's with a rational type problem, and that's what we're looking at today. Vertical asymptote, remember, a curve has that if the limit at A approaches positive or negative infinity. So if I'm approaching a number, if it goes to positive or negative infinity, I have a vertical asymptote. And we know that for a rational function, that's where the denominator equals 0. And a horizontal asymptote, if the function approaches a number, when it goes to positive or negative infinity. Okay. Steps 1 through 3 here. This is all done with f of x. So steps 1 through 3 are done with f of x. You can find the domain, you can find the asymptotes, and you can find the x and y intercepts with f of x. So honestly, steps 1 through 3 are nothing new to calculus and stuff that you've done before in the past. And usually with steps 1 through 3, you've been able to graph the function just fine, but calculus kind of helps refine that process just a little bit. Now the next steps are using the derivatives. Okay, so for instance, numbers 4 and 5 here, these are dealing with f prime of x, which we've already learned in previous lessons. So once we find everything we can with the original function, we move on to the derivative function. We find critical numbers by setting it equal to 0 or where it's not existent. Okay? We're trying to locate all of the possible maxes and mins from our critical numbers. And it's the interval between the critical numbers that we can identify the increasing and decreasing intervals. Okay? So remember, the first derivative is helpful for increasing and decreasing and maxes and mins. And then when we're done with everything we can do with the first derivative, we move on to the second derivative. So steps 6 and 7 here are talking about the second derivative. Okay. We find that, and we find setting it equal to 0 or does not exist, we can find inflection points. It's where we change concavity. Okay? And again, it's where the second derivative is equal to 0 or does not exist. And we determine the intervals of concavity using pretty much the same concept as increasing and decreasing. We do the number line for the second derivative. So where it's positive, it's concave up, where it's negative, it's concave down. And we use those number lines to help us sketch the curve. Okay? So my goal is to do a couple examples with you, but keep these steps in mind, and I'll kind of label them as we go. We'll see what we can do. Okay. Oh, one other thing that we're going to learn today. This goes with steps number 1 through 3 with the original function. Slant asymptotes are going to be something that pops up as well, not just horizontal and vertical. So just remember that slant asymptotes occur when the degree of the numerator is 1 more than the degree of the denominator. What that means is, like for instance, x squared plus 1 divided by x, okay? The degree of the numerator is 1 more than the degree of the denominator, meaning if I were to divide that, I'd be left with a linear function. That linear function happens to be the slant asymptote, okay? So we're going to bring back some old school math here. We're going to simplify using long division on the rational expression. The equation of the slant asymptote is y equals the quotient minus the remainder. Okay? So we're going to do examples of all this. We'll see it all in action. Let's do 2. Let's start off with f of x equals 3x plus 2 over 2x minus 1. And just kind of sticking with the steps that we talked about earlier. Let's do all the stuff that we can figure out with just f of x. Let's start off with, I'm going to try to organize this as best as I possibly can. I'll just kind of go in order here. Let's start off with everything that we can figure out with f of x. So number 1, we can talk about the domain. That may be helpful. The domain for a rational can be any number but what makes the denominator 0, right? So in this case, it looks like that's going to be equal to 2. Right? So in this case, I'd say the domain is negative infinity to 2, and as well as 2 to infinity. Okay. All right, so that's kind of like step 1, and that's just review. We know that we're going to have some lines, some values everywhere but 2. So I know you already probably realized that's going to be a vertical asymptote, but we'll get to that. Number 2, let's just for practice find the x and y intercepts. Sometimes that's helpful when graphing these functions. So remember how x-intercept works. X-intercept is where it crosses the y-axis. So it's where y is equal to 0. 3x plus 2 over 2x minus 4 equals 0. And remember, that's just where the top equals 0. So 3x plus 2 equals 0, or x equals negative 2/3. Okay? So we have my x-intercept at negative 2/3, comma 0. And y-intercept is always pretty easy to find. That's just whenever you plug 0 in for x. And if I plug 0 in for x in this equation, I get 2 over negative 4, or negative 1/2. Okay? So we got the domain, we got the x and y intercepts, so those are 2 points that we can graph. And then the last thing we can discuss is number 3 with the original function is the horizontal and vertical asymptotes. So we already stated that the vertical asymptote occurs at x equals 2. All right, that's just where we have a vertical asymptote, but it's what makes the denominator 0. And remember, we know how to do horizontal asymptote. That's a limit type problem. Remember, it's just there's a rule for that, and it's comparing the highest power on top with the highest power on bottom. And in this case, they're both 1, so we take the leading coefficient. So that means my horizontal asymptote is y equals 3/2. So we got a horizontal asymptote, we got a vertical asymptote, and we got an x and y intercept. So all stuff that we've used in the past to already graph this, and honestly, we could pretty much graph it based off of this. But now we're going to talk about some more information that's really going to narrow it down for us. Okay. All right, so we got all that information. Maybe I'll do it this way. So I'll put a little line right here, and in blue, I'll do everything we can figure out from the first derivative. Okay? All right, so from the first derivative, we'll find the derivative first. So remember that the function was 3x plus 2 over 2x minus 4. If I find the derivative, that's going to be equal to low, which is 2x minus 4, d high, which is just 3, minus high, which is 3x plus 2, d low, which is going to be just 2, all over low, or 2x minus 4 squared. And since we're going to be taking the second derivative eventually, and we're plugging some points into here, maybe it's helpful to simplify. Okay, so this is equal to 6x minus 12 minus 6x minus 4. And those 6x and negative 6x cancels out. So really what I'm left with is negative 16 over 2x minus 4 quantity squared. Now, remember what we do with the first derivative and what we do with the second derivative is we're finding critical points and inflection points. We're finding where it equals 0. Okay? 0 or, I'm sorry, for critical points, 0 or does not exist. Now, it looks like there's no points that make this 0. There's nothing I can plug in on top that makes it 0, but there is something on bottom that I can plug in that makes it 0, makes it undefined. And that would be x equals 2. So x equals 2 is a critical point. Right? And we already know that x equals 2 is undefined in the original problem, so it's not necessarily going to be a point, but it is going to be a vertical asymptote. Okay? So whenever we do that, whenever we identify all our critical points, we start to make a number line. All right? And trying to figure out the best way to space this out for us. All right, I'll just do my number line right here. F prime of x. Actually, you know what? I want to do my number line below because we're going to be using our number line to graph here in a sec. So I'm going to do it right here. Okay. I'm going to say that we got f prime of x, and I'm going to have f double prime of x. Remember how important this number line is for graphing. I think it's good to have pretty close by. So we have 2 as the only critical point. It happens to be a point that's undefined. Now, if I want to test points to the left and right of that, I test it by looking at values in the first derivative. So I'm going to test points like 1 and 3 and see what happens. Well, if I plug 1 or 3 in the denominator there, I'm squaring it. It's always going to be positive. It's always going to be a negative number divided by a positive number, which is always negative. No matter what number I test, it's going to be negative. That means that this function is always decreasing, right? Negative slopes mean it's always decreasing. Okay. All right, so what I'm going to do now in green, is take the derivative of this. Now I got the second derivative. And remember that I always rewrite, if I had a constant on top, I don't do quotient rule. I always rewrite it as negative 16 2x minus 4 to the negative second. Makes the derivative a whole lot easier. So doing chain rule, bringing the negative 2 down, I have positive 32, 2x minus 4 to the negative third, and then multiplied by the derivative of the inside is 2. So what I'm left with is 64 on top, 2x minus 4 to the positive third power. And that's what the second derivative equals. So to identify inflection points, what I'm going to do is I'm going to set this equal to 0 or does not exist and solve. And you're going to notice, just like before, there is no values that make it 0, but there is values that make it undefined. And again, that's going to be x equals 2. So x equals 2 is an inflection point as well as a critical point. Okay. So actually on my number line here, what I'm going to do is I'm going to plug in 2 again, and I'm going to test points to the left and right of that. So if you notice, because it is cubed, if I plug a 1 into that, I get a negative number on bottom, and a positive divided by negative is negative. And any number greater than 2 is going to give me a positive number, and a positive divided by a positive is positive. Okay. So we have found a bunch of information here. We found inflection points, we found critical points, and they happen to both be at 2, which means the vertical asymptote. We found out that it is decreasing and decreasing. We found that it was concave down and concave up. So we're going to use all of this information to graph this function. Okay? All right, so using all the information we got, let's graph this bad boy out. So you can just draw a generic graph. Looks like we got a lot of information around 2 here, so we're going to go to 2 right now. And I like to go in order of all the stuff I found. So I like to find, first of all, I want to plug in all the stuff I found from the original function, which the stuff I found, like I figured out that I have a vertical asymptote at 2. So I'm going to do a little dotted line at 2. Okay. I also figured out that we have a horizontal asymptote at 3/2. So if I go up 1, 2, 3/2 is right in the middle of that. So I'll do this. Okay. And I also found an x-intercept at -2/3, 0. So here's -1, -2/3 is about right here, 0. And I also found a y-intercept at 0, -1/2. So here's -1, -1/2 is like right here. Okay, so I got that so far. So I believe that's everything that we found out from the original function. Now everything else is on this number line for me, f prime and f double prime, just like before. I know this function is always decreasing. So decreasing means that the function is always getting lower. Okay, and I also know that at 2 we have a change in concavity. All right, so I know you know what the shape already looks like. Let's make this work. If I knew it was just decreasing, I just have a bunch of straight lines, but the concave down and the concave up tells me the curvature. We know how vertical and horizontal lines work. So a rational function goes along the horizontal asymptote because it's coming from infinity. It's going to go through these 2 points, okay? And because 2 and 2 right here are both undefined and we can't actually plot those points, it's a vertical asymptote, we're just going to follow the curvature all the way down the vertical asymptote. Okay? So look, I mean, we followed along the lines, we went through our 2 points, and notice how it's concave down. Okay? Well, to the right of 2 is concave up, and the only way to trace along these asymptotes with concave up is to come from positive infinity to our asymptotes. So you can see concave up, to the left of 2, it's concave down. And again, you probably didn't need that information to graph that, but it was definitely very helpful to know. Okay? Concave down from negative infinity to 2, concave up from 2 to infinity. And notice how the function is always decreasing. Smaller, 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 smaller. From here, it's going smaller, smaller, smaller. The function is always getting smaller, always having a negative sign. So that's all the common information you're going to see with rationals. All right. Now I want to do one more, and then we'll save the last 2 for class. Okay. So it says sketch the graph of x squared over x minus 1. Let's go through our steps again. Let's do everything we can with the function itself, then the first derivative, and then the second derivative. So what I'm going to do is maybe I'll trying to organize this as nice as I can without y'all here. How about I'll do the function right here in green. I'll do the first function right here in green. And we'll just go down the steps that we talked about. Okay? I think it's helpful to know the domain. It's not the most necessary step, but it's helpful. And this is a rational, so everything is defined but what makes the bottom 0. I think we can see that that's going to be, let's see, 1 is not going to make the bottom 0, right? So we're going to say negative infinity to 1 and 1 to infinity. We can also identify stuff like the x-intercept and the y-intercept. And if I plug 0 in for x, okay, 0 divided by 0 minus 1 is just 0. And if I were to plug in 0 for y and solve, the only thing that makes the top bottom is 0. So again, 0 in for y, x is going to have to be 0. 0 squared equals 0. So it looks like we only have one point where it crosses both axes, and that's just at the origin. So that's helpful information. All right, let's go to step 3 with the asymptotes. Vertical asymptote, we already know, is what makes the bottom 0. So that's x equals 1. We know we're going to have a dotted vertical line there. The horizontal asymptote. Okay, look at this. Horizontal asymptote, we have the numerator that is greater than the denominator, meaning that there is no horizontal asymptote. Whenever we don't have a horizontal asymptote, we usually have a slant asymptote. Notice the difference in the powers, 2 to 1. So we do have a slant asymptote. So that's what I would like for us to find next. There is no horizontal, but there is a slant. And a slant is like a horizontal asymptote, it's just tilted a little bit. And it comes by finding the quotient of x squared minus, or x squared divided by x minus 1. So we're going to have to refresh ourselves on long division. Let's see here. I got x squared that's being divided by x minus 1. And just a little crash course refresher on this. Remember that you're trying to figure out what you got to multiply x by to get to x squared. And that's x. So you multiply it back through to x and negative 1, and you get x squared, and you get negative x. And you subtract. Okay. The x squareds cancel, and 0x minus negative x actually gives you positive x. Okay. So then you're trying to figure out, okay, what you got to multiply? You start the whole process over again. What do you got to multiply x by to get x? And that's just 1. So if I multiply 1 back through, I get x. Oops. I get x, and 1 times negative 1 is negative 1. So I subtract, that goes to 0, and I'm left with just minus negative, positive 1 left over. So x squared divided by x minus 1 is x plus 1, with a remainder of 1 left over. Okay? Remember, we always put the remainder over what we were originally dividing by. What a slant asymptote is the quotient without the remainder. So my slant asymptote in this case is y equals x plus 1. So we have that as another dotted line that our graph is constrained by. Okay. So there we go. There we have it. That is the slant asymptote, vertical asymptote, intercepts, and domain. Stuff that we have seen before. Okay, now let's figure out everything that we can find from the first derivative. All right, so we're going to find the first derivative. I'm going to try to squeeze these in columns here as I can. The first derivative is low d high minus high d low, all over low low. We got the function right here. So that's low d high minus high d low, all over low low. And I think it's a good idea to simplify this before we set it equal to 0. So if I distribute, I get 2x squared minus 2x minus x squared, all over x minus 1 squared. And this equals, let's see, what does that simplify to on top? looks like x squared minus 2x all over x minus 1 squared. Okay? So we got the first derivative. And remember, from the first derivative, we use that to find increasing, decreasing, and maxes and mins. So I think it's good if we set this equal to 0 and does not exist to solve. Okay. So for my critical points, what I'm going to do is I'm going to set the top equal to 0. So I'm going to go ahead and factor that as x minus 2 times x. Set that equal to 0. And I'm going to set x minus 1 squared equal to 0. And I get x equals 0, I get x equals 2, and I get x equals 1. So I got 3 critical points, 2 that makes it 0 and 1 that makes it undefined. We just know that the 1 is going to be a vertical asymptote. It's the 0 and the 2 that do work in the original function. So I'm going to put those on my number line, and we're going to go ahead and look at what those critical points could possibly be. So I'm going to do that in blue. Okay. So what we have is f prime of x. I'm going to put, let's see, 0, 1, and 2. And we're going to test some points by plugging them into my derivative function, which is this function here. So maybe test like -1 and see what you get. For sake of time, I'm going to go ahead and kind of tell you what those values are going to be. If I plug in anything negative into this, so first of all, it's always going to make the bottom positive. Okay, so you're really looking at the top. If I plug in -1, I end up getting a negative number. If I plug in like 0.5, I end up getting, oh, I'm sorry, I got a positive number, right? Because, yeah, that would be a positive number. Sorry. If I plug in like 0.5, I get a negative number. If I plug in -0.5 or +0.5, I get a negative number. And anything greater than 2 is going to be a positive number. Okay? And again, I was just testing points in this function here. So what I want to do now is do the same thing, but for the second derivative. I'll do this in black, and we'll find all those intervals on the number line below as well. So f double prime is equal to, that's low d high, so we're going to do low, which is x minus 1 squared, d high, which is 2x minus 2, so low d high, minus high, which is x squared minus 2x. D low, which is going, so low d high minus high d low is going to be 2x minus 1, and then the derivative of the inside is just 1, so we can leave it like that. So that's low d high minus high d low, all over low low, which is going to be x minus 1 to the 4th. Now, before I keep going, I just want to say, for sake of time, we could simplify out the entire top, and we could, you're going to see some nice things simplify out, but actually what happens here is pretty cool. All these quantities have an x minus 1 in common. So I can cross out one of those from the top and the bottom. So what I'm left with is x minus 1, 2x minus 2 minus x squared minus 2x times 2 all over x minus 1 cubed. And if I were to simplify this down just a little bit more, it actually simplifies out really nicely, and we end up with 2 over x minus 1 cubed. Okay? So that is my second derivative. And the second derivative, if I set it equal to 0 or does not exist, the only point that we get is 1. That is a vertical asymptote that we already found at the beginning. It happens to be a inflection point as well. If I test points to the left of 1, I get negative numbers. And you can pause the video and try that now. Plug in numbers to the left of 1. It's going to be a negative number. Numbers to the right of 1 are going to be a positive number. Okay. So, okay, for the last, I'm a little bit over 30 minutes, but I'm going to finish this graph real quick, and I'm going to shut up. Let's graph it. Okay. Just like before, it looks like I'm centered around 1 here. Okay, at 1, we have a vertical asymptote. So we're going to plot everything we found from the original function. We got a vertical asymptote of 1. We know that the only intercept point is at 0. Okay, and lastly, we know we have a slant asymptote. The slant asymptote was x plus 1, and we know how to graph x plus 1. X plus 1 is starting at 0, 1, we go up 1 over 1, up 1 over 1, so it kind of, this is what this graph looks like. So my function is constrained by the vertical asymptote and the horizontal asymptote, or the slant asymptote. Now, the only other thing that we have now is we know that at 0 and at 2, okay, we have a maximum here because it goes from positive to negative, and a minimum here because it goes from negative to positive. And if you graph this, I'm sure you can see this right here. But we know at 0, 0, we already have that point right here. It's a maximum. So if I follow along my slant asymptote, hit the maximum, and go down, you can see it follows the concavity as well. It's concave down as it goes along. The asymptote goes to my maximum and goes down. It's concave down. And then it's concave up. Ooh, that's not good. It's concave up. So at 2, we have a minimum. And if I plug 2 into this function, it's going to be somewhere right here, okay? And that's going to be a minimum value that's concave up like a cup. See, there we go. Huh? That's our function. And I'll go over more of this stuff later. So we combine the concavity with the max and the min, the slant asymptotes, all that information together. Okay? We knew that it had to be constrained here. And we could have definitely, if I had more time in the video, I would have actually figured out what this point was. We could figure out that this is 2 something, and we know we're on this side of the slant asymptote. All right, well, I'm over 30 minutes. I'll re-explain any of this that we need to later. I hope that y'all have a fantastic day as usual. Smiley face, star, heart.